Wasn't that incredible? Just incredible. I want to begin by saying that if this professor gig doesn't work out for you guys, there might be a show that we start, The Real Professors of Southern California. Would anybody watch that? Brigitte, the first question goes to you. So you've been working on this for some time. It's a massive undertaking. Tell us about the first time that you really thought that there was a there, that you recognized that this might actually happen.
Well, Donald would probably like me to say when he told me.
Okay.
But it was really maybe 3-4 years in, we had a lunch together, and I was getting an update, and there was just a moment, I was watching the three of you, and there was just magic. And I knew they were really going to do it. And and that's when it clicked.
Yeah, I think there was one thing that really shows in this movie, and that's the importance of collaboration and how three, not totally dissimilar, but pretty far apart activities can come together and really create something of just striking beauty and impact. And it's amazing for one to see this collaboration bear fruit in the movie. Harry, this next question's for you. Can you tell us, what is it like to be part of a high-performing team of stellar colleagues kicking ass?
Just another day at Caltech.
Yeah, right.
No, seriously, it's been the honor of a lifetime to work with these guys. And I didn't imagine when I didn't know that much about Caltech when I was growing up, and I only learned about it really late, as I was starting to form my professional career. But I didn't appreciate the easy, frictionless collaboration opportunity, and this project is a really great example of it.
Do you think that's part of the California culture, or was it Caltech specifically?
No, I don't think it's specific to Caltech. I think there is something in the water in California, and I think that's why we're all here.
Yeah, that's well said. Thank you.
But one unique thing about that that collaboration, in addition to all the pieces, where the professors are working together, was the way. The thing that struck me. I had joined Caltech a few years earlier from Cambridge University in England, and the involvement of the Caltech president in bringing us to a set of lunches and meetings with Donald and Brigitte, where we were presenting our ideas. That is not something that in a big university can happen easily, but perhaps in a university that is small and has large ambitions can happen.
That's fantastic. That's well said. Ali, this next question is for you. You mentioned democratization of electricity as a critical part of what you saw in this project. And I'm just wondering if you could share with us, what are the top 2 or 3 applications that you could envision as a result of this technology enabling?
Right. So that really goes back to the technology's capability of sending energy where you want, when you want, and as much as you want. And this basically gives you carte blanche in terms of what you can access. But I think primarily, really, as I mentioned in the movie, the disaster areas is the first one that comes to mind, because that is where you have absolutely no other choice. And the other part of the story is, in general, wherever you cannot get the energy there easily, a lot of this goes back to the infrastructure that you need to get. And people forget about the footprint and the amount of infrastructure cost of getting those high voltage power transmission lines across the land. So that ability for disaster areas and hard to get to areas is the primary application. But the hope is that once you get past those, with scale, you can reduce the cost, and then you can make it accessible anywhere you want, and then go and deal with the cities and towns.
Got it. Harry, do you have a favorite?
A favorite aspect about
just favorite application for the new energy source?
Well, I guess I would say that the opportunity to go to developing, Ali brought this up actually in the film as well. When Africa built out a telecom network, they didn't build copper wires going across the landscape like they did. They leapfrogged. They went directly to wireless. And you can envision that could happen. So I've been to a number of places in Africa, and there isn't copper wire power infrastructure across the entire continent. There's no grid across the continent. You could imagine this being something that would really rapidly enable power in developing parts of the world.
When you get it to the ground, can you hop it along the terrestrial plane?
It is possible. I mean, and that's part of the other part of this technology that we didn't talk about in this movie is that a lot of this is applicable to terrestrial applications, basically just sending energy to over distances. One of the things that I'm also co-founder of a company that does it for terrestrial applications, and one of the things they have drones that are in flight 24/7.
Where is the home of that company?
So that company is in Pasadena, but my previous company was actually in Irvine.
Oh, that's what I was hoping to say.
Yes, it was in Irvine, and that's a company that shipped like hundreds of millions of units. But yeah, so the ability to send this energy over hundreds of feet, power and charge drones and keep them flying. So there's a lot of applications from your cell phones and all those things.
Yeah.
So going back to the question about hopping, it enables, you can send it. It's like, you can think about it as a power distribution network, that you have the high power ones going to the distribution network, distribution centers, and then you can break it down and then lower the voltage and distribute it. So you can eventually have an ecosystem of wireless power.
That is so cool. Sergio, do you have a favorite application for the space-based power?
Well, my fun is the lightest structures. So for me, the favorite applications is that every spacecraft is going to be the kind of systems that we have developed, but they are so much cheaper and so much lighter that they gradually become pervasive at greater scales.
Brigitte, do you have one? The favorite application?
We could be powering Irvine.
Yeah, right now. Stephen?
We could be powering the entire Earth.
Yeah.
Every
So my
day.
favorite is desal. So I want a desalinization plant next to the beautiful ocean and no power lines next to it.
Exactly.
So
Can you throw in one more?
Yeah.
It's an interesting one. On the moon, because the day and night on the moon are very long. So if you have a station on the moon, you're in the dark for 14 days, and that allows you to send the power wirelessly there.
Very cool. Sergio, the next question for you. Like you mentioned origami in the movie, and it's beautiful to see these structures unfold, and they look to me like flowers. They're just spectacular. When did you start playing around with origami as a tool?
The way it happened is that as I was finishing my PhD, I had an opportunity to visit Koryo Miura, who's a Japanese professor at the University of Tokyo. He actually had two jobs, I discovered. One is at the university, the other one is at the Japanese Space Agency. And he was designing unique structures. And by the way, some of you will know about Miura Ori. He is the inventor of Miura Ori. And that was my first exposure. And it's a highly, highly periodic type of solution that they devised. And I became, as it were, knowledgeable about that particular scheme because over the years I started collaborating with Koryo Miura, and then later on we wrote a book together. So that was my first exposure, and by knowing so much about one particular kind of origami, I then started thinking about other ways of doing it. By the way, what I do in the space solar power is called kirigami, because you make cuts in the sheets, and you are allowed greater freedom in the solutions because the pieces have been separated. Yeah. But traditional Japanese origami does not have cuts.
Did you make paper airplanes as a kid?
Yeah, not so much.
No, really.
I used to do Legos.
Legos.
Yeah.
I made paper airplanes. I made all sorts of paper airplanes. I loved folding paper. Stephen, this question's for you. So you've built a lot of stories around, all sorts of stuff. How do you know when the story is magical, when it's going to capture the attention of people?
Ooh, well, it starts with the characters.
The characters?
Yeah.
No offense, guys.
With the people. The characters. It starts with them, and it starts with their passion. Because even when we have technology that's amazing, it always starts with humans. I know AI is going to do different things, but it really starts with people. And if we're doing a documentary, people like to relate to people. And as you can see here, we purposely made this positive. And these guys worked really hard. And this one was a case in point. When I met them originally, Brigitte, we had lunch together, and they were enthusiastic, finishing each other's sentences, and I was just jumped on board. And if they believed it and they were doing it, I'm there with them. And I think that makes a good film.
But when we started, it wasn't this film.
No.
So when we started, we were so focused on the scientists. I mean, we asked them for their baby photos. We wanted to do it all about the making of a scientist at Caltech.
We can use that in the show afterwards.
And so we had a film called Equilibrium. It was an hour and 45 minutes. It was very long. We were trying to figure out how to edit it. And Equilibrium, I love that title because the three of them, when they came together to go to Cape Canaveral for their payload, the weight of each of their experiments was exactly the same.
Oh, no way.
They were in perfect equilibrium. And I thought that was so exciting. But that wasn't the right film. It became Bright Harvest really after the breakthrough and after the NASA report. And there were several other things where I just really felt that the story needed to be shared because more people needed to be aware of what's going on. I mean, this is promising.
Let's talk about that NASA report. It's a pivotal moment in the history of this activity, and it's not really fully fleshed out. Can you share with us a little bit more about that moment?
So right after they had their breakthrough, which was extraordinary, there was a NASA report coming out that like space enthusiasts from all around wanted to read, and it was about the viability of space-based solar energy. And by design, the work that you've done was going to always be at the cost of the current rate of electricity. It was supposed to be economical, so this is by design. And somehow, the person that put the report together at NASA managed to pick all of the worst possible possibilities, and they were combined together. And then on top of that, I mean, just to add to it, they didn't even include all of the data from this project. They used pre-existing space flying objects. They didn't use Sergio's lightweight solar apparatus. And so they said it was not economically viable. And that was really the trigger, because when that happened, I mean, and the fact that they had this extraordinary breakthrough, and no one came, because probably of this report, among other things, I just knew we had to share the story. And that's how it became Bright Harvest.
Thank you. That must have infuriated you guys. Sergio?
Yeah, so I mean, there are two things that happened. I mean, Brigitte gave you her side of the story. We were infuriated, but, we work in academia, so our way of doing things is to write papers. So we finally got our act together. I mean, we had previously written a paper that talked about all of our ideas and so on. And it was so long that we sent it to a journal, and they said, well, you've really got to cut it down. This is too long. So anyway, it just kind of stayed there, and we left it there. But when the NASA report came out, we were so upset that we decided we would write a paper that everybody can read, or people who are seriously willing to put the time. We would explain it clearly, rather compactly. And so actually, that paper got published last year. It's in a journal called Joule. And if you want to read about it, I mean, really what is important about that paper is that it actually makes very clearly the economic argument.
Yeah.
Because even though that is not our field, we actually spend a lot of time trying to understand the way you put together all this stuff in a way that is super economical. And we deliver that estimate in this paper.
One of the things that we had talked about previously in prep for this is the elements that we have to bring to the table to really get this stuff going. And there were three topics that came up over and over again: regulatory, supply chain, and capital access. Harry, what is your take on the regulatory environment? Is there receptivity in Washington for this stuff? Is there an appetite for new sustainable energy sources?
Well, okay, I think there are a couple things going on simultaneously. One is that there is concern about, particularly in low Earth orbit, space being very crowded and potentially filled with quote-unquote space junk to the point where things collide with one another and create a sort of dangerous environment for spacecraft, at least in low Earth orbit. But at the same time, there's this burgeoning now commercial space activity going on, which is giving rise to all these things in low Earth orbit. So, and they are all abiding by government regulations and international agreements as things are developed. So these two things are going on at the same time. So there are regulatory aspects to doing this, and particularly for space solar power. We talked a little bit in the film about how do you deliver power safely. How do you do it in a way that is resilient? All of those things are important. The Federal Communications Commission allocates certain specific frequency bands, and you have to transmit within those bands. So these are all aspects that come into it. But I think one of the things that happened too is that space has gone from being a specialized boutique gold brick business sponsored by the government to build spacecraft for defense, intelligence, space exploration, and so forth. Pretty expensive, but everybody's willing to pay the price. To being something that is modular, scalable, manufacturable, literally
Reusable
3D
rockets.
printed in many cases. And that's a completely different paradigm. And that's the one, in the film I said that one of the things that I think we did that was most important was to foster a component-led revolution. And what I mean by that is that each of us had designed modular components that when you put together in a scalable way are manufacturable. And if you look at all technologies like integrated circuits, solar panels on Earth, magnetic hard drives, telecom, they're all exponential businesses. And they all rely on building manufacturable, scalable components that work together. So instead of thinking about space solar power as being this gargantuan object that you build in a boutique fashion, build it in this scalable, modular way. And that, we think, is the ultimate pathway to success.
That is so beautifully said. Sergio, you started companies in this region for power and power transmission. Can Southern California be the home to this industry?
Absolutely, I think this is the perfect place for it because it's just it has a combination of space technology and also the solid state and electronics technology. I mean, you have in Southern California, you have companies like Broadcom and all those things that have been, a lot of electronic systems and integrated systems that are happening in, particularly in Orange County and Irvine, that are the core technologies that enable that scalability, that the system that we designed was really scalable to the fabric. And that combination, that culmination of and convergence of the space technology, you have places like JPL, you have all of the space industry and aerospace industry, and you have all of the electronics industry. So I think that this is actually the perfect place to do it.
I think that's well said. And part of the scaling up, it allows the technologies to have alternative uses. They're not specifically built for a single space application. They're not quite off the shelf, but damn near.
Exactly.
And that's pretty exciting.
Yeah. And some examples of those things are, for example, the things that we have thought about for a long time within these technologies are servers in space, for example. Nowadays, a lot of energy is required to have this computational server with the emergence of AI. And this is something that we've actually talked about and filed patents on like almost 10 years ago, where you collect the energy and then you have the cooling in space, and all you do is just launch the job and get the response, and all the processing is done in space.
Yep. It's going to happen. Brigitte, we talked about those three elements, regulatory, capital access, and supply chain. Like what does your gut tell you is the most critical of those three?
Well, they're all critical, so everything has to work together. So on the regulatory front, there's the fact that there's no comprehensive space law. And the last treaty was from 1967. It never contemplated space-based solar energy. So there's no property rights for the energy being produced in space. There's real estate's important. And the allocation of the slots where it is in geo-orbit or where it's positioned is really important because some areas are better than others. And then so there's no rights for that. So there needs to be work on that level. And also for space traffic and debris management, there is no international, there's no binding rules on the international front, so there's a lot of work that has to be done on the regulatory side.
Yeah, I think that this type of technical driver gives us all an opportunity to contribute to some massive worldwide activity, worldwide impact. And there really aren't a lot of projects like that. There are a lot of projects where you build a bridge, but this spans the globe. We were using technology from Japan and Germany, and it's a wonderful testament to human ingenuity to pull this off. And it's really wonderful to see that. Harry, this next question's for you. In the film, you talk about only wanting to work on projects at this stage of your life that make an impact. And about a third of our audience, pardon me, is young, emerging, professionals. Can you just share with us the epiphany you had at that moment when you were like, yeah, from here on out, I'm gonna do impact projects?
Well, I think, at least when I was young, I felt immortal. I was going to live forever. I didn't really think about the finitude of anything. As you get a little bit older, you realize you have a finite amount of time, but you also begin to appreciate your own agency, your own ability to do things. And everybody has agency. And what has been just amazing in my experience as a Caltech faculty member is to work with young people who come in and they are just totally committed. They absolutely want to work on things that have impact and agency. They're not sure exactly how to do it. And that's part of our job, is to figure out how to point some directions. But I think that is, I think young people are hungry for those kinds of opportunities. And that's why I think this is a great vehicle for creating those kinds of opportunities.
That's just fantastic. Who read Popular Science as a kid? Sergio? Well, you had the equivalent of that, right? Yeah. No? Favorite science fiction writer?
Robert Heinlein.
Oh, that's a good one. Brigitte?
I don't have one. I didn't read science
You
fiction.
didn't read? It's never too late to pick up. Sergio?
None.
None?
I guess, given the film, we're probably obliged to say Isaac Asimov.
Isaac Asimov, right.
But
He's great too.
But
yeah.
actually, in reality, it's Philip K. Dick.
Yeah, that's
Yeah.
good. That's a deep cut. Ali?
Greg Egan.
That's another one. All right, so we're at that time in the talk that before we open up to the audience, we're going to do a speed round. And the speed round is I throw out a word, and I'm going to point to you, and I'm going to ask you to give me a little bit of a short, brief answer on, Stephen, impact.
Impact. We're hoping this film has impact. That's short, and that's what we want.
That's good. Harry, exponential growth.
Solar.
Solar, good, okay. Ali, wave interference.
Power where you need, when you need, and as much as you need.
God, you guys are rocking this. Sergio, dispatchable power.
Ask Ali to take care of it.
Ali, dispatchable power.
Focus.
Origami.
Make it from thin sheets of carbon fiber.
Start there, right? Brigitte, tenacity.
The three of them.
Three of them, well, gets well said. Harry, agency.
Creating your own opportunities.
All right, Stephen, you get the last word on the speed round. Narrative.
Narrative. Storytelling, which is what we're doing here. We played this story. This is their story. And stories can have very positive consequences because it can inspire and make things better.
That's where we are going to turn it over to the audience. That is perfectly said. The audience is open. The mics are open. I'll ask you to please introduce yourself and give me your question. Goran is pointing 2 microphones.
I'd love some.
I think I saw Brett Sanders. Is Brett here? There he is, Brett. Brett is our head of the sustainability collaboration at UC Irvine and responsible for UC Irvine's efforts in the area of sustainability. Brett, you've sat down and seen our discussion. Share with us your thoughts on what you've learned and where we should go from here together.
Well, yeah, thank you, Errol. Thank you to all of you for this incredible story. It's an inspiration. I think, I saw the word hope in there, and I think we all need a lot of hope today, don't we? Yeah, so as Errol mentioned, I was asked by the provost last year to start a new initiative on this campus around climate and sustainability. And we have enormous strengths on the campus across many different fields, from the physical sciences to the biological sciences, engineering, social sciences, you know, the arts, humanities, social ecology, law. And we're thinking we have all these pockets of strength, all relevant to climate. But we need to find a way to sort of position ourselves to put the pieces together in such a way that we have greater impact. And we've come up with a recipe about the elements that we think are important, but I'd love to run those past you because I saw all these parallels between what you're doing and how we've constructed this initiative, and I would just love to know as a question, like, what do you think maybe is missing? So what we've done is we said, if you want to come to us and work on, sort of be supported with the project, the first thing you need to do is come with multiple disciplines around a challenge, okay? So we're not interested in two people in the same department who've worked together. We want to see some like disparate perspectives coming together. That's number one. The second thing is that you need to come forward with external partners that care about what you're doing. You know, we're interested in sort of the boots on the ground, the experience that those people are having, and the relevance of our scientific work to governments, to the private sector, to non-governmental organizations. So we want that. We want the external partners. Thirdly, we want to see you guys have impact on education. We want to see you engaging students. And your film beautifully shows like the spark, the energy that happens when you pull students together. And so we've got the piece around multiple disciplines, we've got the piece around external partners, we've got the piece around education, and that so far is our recipe. And I want to tell you, is there something missing? I'd love to know your perspective of what else does it take to have like a really effective and successful collaboration.
Thank you, Brett. Let's go to Sergio first, if I may. Sure. Sergio, you mentioned recipe in the movie and how you were building a new recipe. So I'm going to ask you to please take the first stab at that.
Yes, I said that in the context of a specific project already had a direction. Right now, this is about the direction. Mm-hmm. And what is a good project. And I think, you know, what you've heard in the movie is the role of Donald Bren. Mm-hmm. Now, you see, this is somebody who is not one of the partners, and he's not thinking, what can I do together with 5 other people? No, it's somebody else who's got, like, looking at this from a perspective that is completely different. Now, it doesn't have to be Donald Bren, because if it is Donald, then perhaps he can also provide the resources. But maybe it can be a group of students. So sometimes we run a project, which is a kind of a crazy project, and the students come up with something really quite strange. Now, in my case, we came up with a project we run in our aerospace class, providing power to Maui. And, you know, do some kind of way of doing power to Maui. And they talked about building a giant version of what I do in space. So I got that idea, and now I actually have a project where I do that. So what I'm saying, ask somebody who is not one of you or like you to actually give the initial spark. I like that.
That's great. So a taste maker, somebody to taste what you're making and take it from there.
Any other thoughts
Ali,
from other
please.
members?
Yeah, sure. So maybe I can start with an anecdote and get back to the idea that I'm trying to tell you. It's a short one. So when my kids were younger, I have 2 children, and then they got into squabbles over toys and all those things. What I told them is that, remember, people are more important than things. So that was something I kept. And I told them the following thing also. So I said, but there's only one thing that's more important than people. And I said, what is it? I said, well, you have to figure it out. So, you know, they went through a kind of long process over many years and all those things. But eventually, what I meant was that ideas, because ideas are more important than people individually because they transcend and transform people. Now, the reason I'm saying this kind of somewhat segues and dovetails with what Sergio said, which is that don't underestimate the power of being able to take a step back, not being driven by the current flow and the directions that are out there, taking a step back and say, okay, if I could do anything I wanted to do, subject to the laws of physics, what are the things that will have the most impact? and start from them. And I've been surprised by the number of things that actually are not that infeasible, that we would not have done if we had to follow what other people told us what the current trends are.
Yeah, I was struck in the film by the way that each of you brought a background, a disciplinary background, but it was a synthesis of those things that led to something magical, right? It was that synthesis. So, yeah. Yeah, did you have thoughts?
I think there's an X factor that every university professor knows, which is that beneath the calm veneer of a faculty confidently charging into the future, there's this guerrilla network of students who are all working together, sometimes subversively, not telling you what they're doing, collaborating, and then they come and tell you afterwards when they've done it. And that is an absolutely key ingredient to the whole process as well.
Well, again, thanks so much for the inspiration and the hope. Appreciate it.
Thank you for the question.
Thank you, Brad. Please.
Afternoon or evening, gentlemen and young lady. Mine's pretty practical. I have two questions. And one, from the standpoint of the audience, and it probably didn't need a rewrite of the paper, but you guys have done these calculations probably and explained them quite a few times. But based on the solar in space and being able to beam it in RF energy to the ground, and however you're controlling that beam pattern and getting past the clouds. Obviously you were in Leo and traveling around the Earth, so that means you've got a certain amount of dwell time. But when you look at the scale of what you showed in the figures, if you were to build that deployable array, how do you translate that into the efficiency of the energy you collected relative to what your losses are at the reception point? In context, how would that translate to the number of homes you could power simultaneously from one of those installations?
Sure. So maybe I can throw some numbers at you. So there are a couple of things. First of all, the question that we didn't talk about in this movie, and I'll try to be brief about this, but is that why do you do this in space? Why don't you put these on Earth? That's the number one question I think everyone asks, including myself. The reason is that in space, if you're in high enough altitude, you don't have day and night, and you don't have the clouds on Earth. The day and night is the biggest one, and you don't have the angles of the sun. So what happens is that you get about 8 times more energy available for the same amount of area that you collect over, if you look at it average over a year. Then what happens is that the recovery efficiency of RF compared to photovoltaics per given area is about a factor of 3 to 4. So now the system we are talking about is something about a kilometer, about like 0.7 miles, 0.6 miles in space on the side, and about the same size on Earth for the full power recovery. You can actually use a smaller one to recover less. So that system can deliver close to hundreds of megawatts, of 50 to 100 megawatts of power. So that's a significant amount of power, megawatts.
At what rate?
At
Rate.
You
could say that's 100 megawatts for 10 years.
Yes.
Right.
Is that
So we
100
assume
megawatts
our
per
system-
hour? Or?
No, megawatt is rate. Watt is joules per second,
Okay.
right? Yeah. So that is the rate itself.
So translate that into what a typical household
So
would
a typical
use.
household, basically, you get, in terms of kilowatt hours, if you have 24/7, you have basically, a year you have about 80,000, 18,000, 19,000, 20,000, let's say, times that. So it's basically, you're talking about like about 50, if I'm doing the calculation, 50 gigawatt hours. And when you charge your car, looking at an electric car, you're looking at something between 50 to 70, 80, or 100 kilowatt hours. So you can convert that that's a large number. That's hundreds of thousands of that.
So, and that's just one of those
That's correct.
installations.
Yes.
From the standpoint of the beam, is it something that is so concentrated that it can be intercepted or blocked fairly easily by something between you and that?
Sergio, does it cook birds?
Yeah, so one way to think about it is the power density on the ground. And our system is not very focused. It is not a laser. It is actually spread out. So you collect the power by increasing the area of the receivers. We call them rectangles. But I want to come back to the point that you were asking about, just to bring additional clarity into that. The way we think about it is, what is the cost of a complete system? There is the people would say it's the cost of launch that is the highest cost.
That's the
Actually,
industry I'm in,
It turns out it isn't. It turns out that the main cost is the cost of the spacecraft, the materials to build all the stuff we need to build. And so we, as I mentioned this earlier when we talked about that article, we had to estimate, even though it is not our field, if we create industries that actually produce all these components, how much would they cost? This is not the same thing as NASA having a mission, because they do unique objects, whereas we are talking about mass production. And so another question related to that is how long will the spacecraft last? So we assumed 10 years, maybe it could be 15 years. You do all of this, and then you come up to an estimate of the power per kilowatt hour, the cost of that. And the answer is, if we started building this stuff so that we run a system in about 10 years, it would be about 10 cents per kilowatt hour. In the future, it could be less.
Okay. Hey there, y'all. My name is Max, and I'm a first-year aerospace student here at UC Irvine. One of my favorite words that I've learned in my brief time studying here is modular. And so here, this film has me wondering, what kind of next steps and modular adjustments are you guys planning to make with your system in potentially powering more solar energy to Earth?
Well, as I indicated, the reason that this is really truly different from other things that have been built in space is that all of the components are scalable and modular. So Ali showed, for example, a flexible circuit board. We have, PV cells, which are, about the size of a small dinner plate, and lightweight structures that are all modular. And that's the key. Any industry that is one of these exponentially growing industries, like all of the electronics industries, all have that character. The tiles themselves are modular too. Previously, people thought about building a gargantuan station that had PV and then huge copper wire interconnects that would come to a centralized power conversion from DC to RF. We do that completely at the tile scale. So there's no DC wiring that goes across the whole structure. You have to deal with timing and communications for a phased array, but there's no DC wiring. So when you build a tile, that's a self-sustaining unit. In fact, if you go on the website for our project, you can see the tile, sunlight coming on the tile, simulated sunlight in the lab, powering a microwave array that lights up an LED just as a tile. So it is modular, and modular is very important.
Thank you. Please.
Hello, good evening, and thank you for all the research that you guys are conducting to be able to make energy more sustainable and accessible. My question is, so I'm sure like most of this audience, we think of solar cells, we think of the traditional rigid structures that you might see in structures such as like the James Webb Space Telescope. So how much more powerful or efficient is the flexible design that you guys made, maybe in comparison to one of the cells that we will see in a space structure that has already been deployed?
Okay, so just to manage your expectations, our cells are going to be slightly less powerful, maybe about 20% less powerful than the most advanced space solar cells today, but they will be a factor of 100 cheaper. In fact, comparable to the cost of cells on Earth. And if you're building kilometer scale structures, nobody has, we talked about capital, nobody has the capital. Currently, the cost of building the power systems we have in space is $10,000 per square meter. Our solar cells have a cost structure of $100 per square meter, like on Earth. And if you're building kilometers in space, you can't build things at $10,000 per square centimeter. So slightly less efficient, a whole lot cheaper, much lighter,
and much more
lower
scalable.
mass per area, much more scalable. Yeah.
And there is another key difference. In the traditional current state-of-the-art, much of that solar cell that you are using is in fact the radiation shielding, which is glass cover. And this glass is actually the vast majority in terms of mass. And what Harry's students are developing is materials which are more radiation tolerant and much lighter shielding. So this is also part of that.
Our last question.
Thank you.
Thanks for your time. I was hoping each of you, Sergio, Harry, and Ali, might be able to speak about ongoing research, what has you excited today in the lab, either related to this project or that has spawned from this project.
15 seconds. Ali, go.
Yeah, synchronizing things across a kilometer at the picosecond time scale. So basically getting on a flexible structure that is floating and formation flying. How do you keep things synchronized?
You did it in 13. Harry, go.
New materials for making tandem radiation-hard manufacturable solar cells called Zintal compounds.
Oh, we call what?
Zintal compounds.
Okay. Sergio.
Transforming the dynamic deployment that you saw that gave me so much trouble into a different scheme that is much more robust.
All right. Thank you. So we are now at the point where I ask each of the panelists to give us their closing comments in all of 30 seconds. Stephen, go.
Well, I know that we were going to have a 1 hour and 45-minute film. I still want to do that, but I'm going to wait until they finish this and this is deployed up there, and I will wait, and I still want to collect all those baby pictures.
I really believe that because this project is born in Southern California, and I'm hoping that the next deployment is out of Southern California, we will be the center of gravity here. And just like the same way Silicon Valley developed, where something is born is usually where it stays. And we can develop industries and jobs, and I think it's a really promising time. I would like to see Southern California be the national hub for space-based solar energy.
Hear, hear.
Okay, so the one thing I would like to say is that we have spent the past 2 or 3 years discussing what is the next step. And we have been focusing in this discussion on the research steps that we are engaging in right now. But we are also starting a commercial effort very, very soon now that is going to apply some of these technologies to what we reckon is the easiest part of the problem, which is lightweight solar arrays for space.
Thank you.
When I was a graduate student at MIT in 1981, the world had a total solar capacity of 1 megawatt.
Wow.
In 2022, the world's solar capacity passed 1 terawatt. And I see the possibility from that lived experience in my lifetime that we could do a similar thing for space solar power.
Ali.
So technology can be a wonderful thing and can be a horrible thing. It's really up to us how we use it. And my hope is that we use it for wonderful things.
Yeah.
That is the note we are going to end it on. Please join me in thanking the panelists one more time.
Thank you.